Hello and welcome to the seventh class on thermodynamics. So,
Good morning, sir.
good morning. I guess the way we are handling thermodynamics might be looking little, looking little tough for you, but if you revise it properly, I don't think and clear your doubts with me. I'm sure, Samidha, good evening. There is no reason why you will have you will not have a good access, good grip on this subject. Rudra was telling me just before some time that he had some doubts on graphs which are appearing in the tests, IIT advanced or main tests. So I have invited him to send me one or two. He has said yes, he will. We will discuss. I'm 101% sure that the extent of the depth of our discussion that we are doing or we have done so far, there will be no reason why you will not be able to analyze those graphs in the arena of thermodynamics. So let me share my screen and slowly start. Are you able to see my screen? Are you able to see
Yes,
my
sir.
screen?
Yes, sir.
Yes, sir.
Before we start today and conclude thermodynamics today and start thermochemistry, it will require maybe 2 classes. This is pure thermochemical calculations, which are also equally important for your exam, particularly in chemistry. But this part, both physics and chemistry, I think Mr. Rudra, who raised about the graphs, must have come in physics questions. Am I correct?
Yes, in chemistry, sir.
Okay. Then we can discuss. Even if you find any question on thermodynamics in physics, feel free to forward it to me for discussion. Because our live program will end after 2 classes. When we complete thermochemistry, our live program will end. Then I can take up your personal doubts, any numerical problem, any conceptual doubt that will be found from any book or while you study any sort from any source, feel free to send it to me for discussion. Well, welcome to those who are watching from the YouTube directly, online, live, and also those who are watching after live program. Here, you just have a glance of what is going on. You can write down, this is of not much required, but these are very interesting things mathematically, uh, that how to integrate. I mean, I'm not saying integrate in mathematical terms, but in literary sense, I'm saying we have to integrate first law with second law. We have a look At any point, if you do not understand, feel tell me in any language you want. Language should not be the barrier between our communication. This is the first law. D is equal to dq. Of course, this dq is a wrong expression. This should be this d cross q, because heat and work, they are not state functions always. Most of the time they are not state functions, they are path dependent functions, so they are not exact differentials. We'll talk about that. Those which are state functions, their differentials are called exact differentials. They follow certain rules. I will tell you what is the Euler's reciprocity rule and the circular rule, and all those things we will have a discussion mathematically, but it's not required. Just listen to me in a very, very lighter uh, mind, to make sure that you are able to understand, simply understand. And if at all, sometime you will be interested to write down, you can write down. We will be looking to the two problems that we had given as homework later. Then we are now putting in place of dq is tds, because ds is equal to q by dt, by t, I'm sorry, by t. So q is equal to tds. Q by dt, dq by dt is cv or cp, but q by t is ds. So so q is equal to tds, and work done is minus b dp. This is chemical convention, and that's what I was saying. Since E or U is a state function, if we express, as I told you, that any state function can be expressed as a function of any other two state functions. So if we express internal energy as a function of entropy and volume, then the exact differential will be requiring this to fulfill. dE is equal to, this is equal to, dE is equal to the del E by del S, one variable at constant, this is constant volume, ds, same ds, plus del E by del V, here the other variable we have taken, at the constant other variable. This is looking like T, but actually it is V. It is V actually in a Roman style. It is V, and nothing other than S and V. In the expression of dE, nothing. This is called exact differential. That in mathematics, maybe in class 12 we will learn what is exact and inexact differential. I am not the authority to explain more than what I am doing. Del E by del S into ds plus del E by del V at constant entropy into dV. The same. Whatever is there in the denominator, same will appear as dV. And if we express dV as a function of, say, U and T, then since volume, I will talk about, say, entropy, which is also a state function. V also is a state function. So ds is equal to, supposing we express as a function of say u and t. So you can write ds is equal to same ds by del u at constant temperature du plus del s by del t at constant internal energy u into dt. So that is the nature of any state function which is an exact differential. I think I should not have, yes, let it be there. Let it be there. Because these things will be required to derive many Maxwell relations, which I will tell you. I don't think they will be required at all, but Maxwell relationships are also very interesting in thermodynamics. Now look, you compare between equation 1 and equation 2. So ds is common. So that T is equal to del E by del S at constant V is equal to T. So we got a relationship from the exact differential nature of E or U. So don't confuse with E, because chemistry people, they often call internal energy as E. So but I am changing to U nowadays and replacing as U. And if you compare, this is dV, this is dV. So P is equal to P is equal to or minus P is equal to del E by del V at constant entropy. Let it be here. It will be required at certain stage. It will be required. Now, let us further blend between first law and second law. This is from second law. Whenever there is entropy, free energy, it is you are in the arena of second law. When there is only internal energy and enthalpy, no entropy, then you are simply, and work done W, then you are in first law. Now we are trying to blend first law and second law. So if you take dH, that is equal to dH minus d whole Ts. In place of H, from the first law you write E plus PV, because that is the definition of H. H is internal energy plus PV energy, and D is outside, minus dTs. So dG is equal to, if you expand, it is equal to dE plus P plus D whole into PV. And now if you expand this, that is T ds plus S dt. So if d of PV means is P dV plus V dP. That thing, because minus sign is there, so both have become minus T into ds minus S into dt. And now again we expand this, P into dV plus V into dP, and the other things are intact. Now let us group TDS, this one, and PdV. So when this is plus sign, when you take minus common, so this becomes minus. So in place of this, we can write dE. Have a look. dE is equal to TDS minus PdV. So TDS minus PdV, the group that we have made, in its place we write dE, so d get cancelled, and ultimately we land with another expression of dG is equal to VdP minus SdT, equation 3. Now we can say at constant pressure, when this term will vanish, then del G by del T, let us bring del T down, is equal to minus S. And if you keep temperature constant, then this term will vanish, and del G by del P at constant temperature will be equal to V. So these two relations we got from the derivation that we have been doing. So if you make del of delta G, the rate of change of delta G with respect to temperature, this here also you write delta G. If you write delta G here, large change in G, that is the change of G in the reaction, delta S. So the Helmholtz equation that you studied gives Helmholtz that del G is equal to del H. I am not putting not. We can have any fixed temperature and pressure. I am in general manner. This del G is not dg by d xi. It's not that. I'm talking of not or any other specified condition. So del H minus T del S. So in place of minus del S, we can write this. So new form of Gibbs-Helmholtz equation becomes, here it becomes plus, and this T is there. So in place of del S, we write del delta Z by del T at constant pressure. So this is another expression for the Gibbs-Helmholtz equation, GB equation. And another, we will be knowing in our electrochemistry program. So consider not in every case. I am not doing not. I am in standard state. So del Z naught, all knots, knots like P naught, coconut, and all knots. I mean, is equal to, as I mentioned to you earlier, that it is n number of electrons involved in the redox process, in the cell reaction, the n factor that we used to call, and Faraday constant 96,500 coulomb, and E is the voltage of that particular cell, which you write V in physics, we write E, and there is a confusion now. This E don't confuse with the internal energy. We blame onto ourselves that E stands for EMF, and E we often take for internal energy. So this is the cell EMF, standard cell, all knots, all knots. So in place of del G, I'm sorry, this del G, we write this small increment del is there, but capital del G we write NFE, and we bring the constant NF outside. So del E by del T at constant pressure. This is called the temperature coefficient of cell EMF. We shall be studying that in our electrochemistry program. So we can also have another expression for the Gibbs-Helmholtz equation del G, and this, since del S is equal to, this was minus, so minus sign will be there, T will be there. In plus of del S we write N F del E by del T. This is the temperature, or what is the rate of change of EMF with respect to temperature. That is the graph of E versus T, the slope of the tangent of the graph of E versus T. So that at constant pressure. So you can take T to here if you like, got it. So I had already given these expressions, but how it came, I am showing the derivation now. Just for fun, you write down these things we have already done. This is another alternative form. If you bring del H here, del H to the left side and T also to the left side, then it will be equal to minus del S from here. Because this minus del S is equal to delta G by del T at constant pressure. So we have written this in minus del S, that is equal to del delta G by delta T. And if you differentiate both the sides, this will be, since we consider del H to be constant, del H by T is variable. At that other time I said del G is very sensitive to temperature, while del H and del S are not. But now I am talking del G by T, that is sensitive. If that varies very significantly, del H remains constant for a narrow temperature range. And we are now going to differentiate these. So we are getting this side, uh, you know, this side we are keeping as such, and this side it will be del H by T square. So the details of the derivation, I mean the differentiation, and I'm not showing. This is the another form you can write down later of uh, Gibbs-Helmholtz equation. You know what I have done here? I have put a T here and del T outside, del T outside. So I have integrated this one, and here it is T square. So I have put T. So this del G by del T, delta G by T at constant pressure, that has become, but how this will be, um, mm, mm, so this differentiation will be not giving T square, because if del H naught is constant, then oh no, no, we will not discuss about the details of differentiation. You can tell me. We will be losing time. We will be losing time. But this is the differentiation of this equation. And on integration, we are getting another, because this t square will become 1 by t. So on integration, we will be getting this one, del g t2 by t2, del g t1 by t1 minus is del hp at constant pressure, 1 by t2 minus 1 by t1. This is the final form to see how del g by t is varying with temperature, not del g by t. So you just tell me, since some of you are very conversant with differentiation, how we got this from this. And of course, you can also tell me how we got uh, this first expression after integration, then taking two different temperatures, because if you integrate this, then this. So this del t by del t will vanish. You will be left with del g by t p. And the right side, since it is t square, it will be t to the power minus 2 plus 1 by minus 2 plus 1. So, and then coming here, so it will be del h by t. And there will be plus sign here. There was minus there, minus here, so plus sign. And taking two different temperatures and subtracting, you will find this is understandable. But how we got this from this, we have to consider. I think it is not that difficult that we cannot do. Uh, this is differentiation. So dxn by dx is equal to n x into n minus 1. So, certain, so that is why, so here uh, So what must have happened? Del by del t, if we do here, and this is already there, del by del g. Okay, we'll look to that. We'll look to that how, because we also love mathematics. This is not a mathematics class, though it's chemistry class, but we love mathematics. I will, you tell me, or I will tell you how this derivation has happened. Okay, then raise your hands, please, if you have so far understood the derivation that we have been doing so far. Oh, I'm having a very uh, complicated mouse handling, so it is not under my control. Some going sometimes weird, uh, so I might be a little slow, which will be better for you. So all of you have understood the derivation. That is a good sign. Now, let me also tell you what is coefficient of thermal expansion of an ideal gas. Uh, this is the rate of change of volume with respect to temperature at constant pressure and constant number of moles. So that is called the coefficient of thermal expansion. Is not required in our chemistry program, alpha, and per unit volume 1 by V del V by del T at constant pressure and number of moles. If you apply Charles' law, V is directly proportional to T at constant P and N. Uh, N constant, not small t. And then if you make a derivation, del V by del T at constant P and N will be equal to K. You bring T down and derive. I mean dV by dt at constant P and U will be equal to K. That means V is equal to KT. So dV by dt is equal to K dt by dt. So this becomes 1 and this becomes dV by dt. At constant P and N has to be there. And since so what is K? So we know that this is equal to K. So alpha is equal to 1 by V into K. So K by V. And therefore we can call it is equal to 1 by T. Why it is 1 by T? Who can tell me? Because you know K by V from this original expression, K by V is equal to 1 by T. This, so K by V, the constant, the proportionality constant. In place of that, we get 1 by T. So the coefficient of thermal expansion of an ideal gas is inversely proportional to the absolute temperature, or alpha T is equal to 1. Alpha T is equal to 1 for an ideal gas. But for real gases, Rudra, you were telling some other day how to find out the work done for a van der Waals gas, I mean real gas, and where the van der Waals constant A, B will come into picture. That I will give you, don't worry. So here I have given for a real gas involving intermolecular attraction or repulsion, as in this alpha T dH, since dH is equal to Cp dt plus, this is for ideal gas, but for real gas extra term will come, V into 1 minus alpha T into dP, this will come, and how it has come we will not know that, but the extra term will be there involving the coefficient of thermal expansion. And when alpha t is equal to 1, that is for ideal gas. If you put alpha t is equal to 1, 1 minus 1, 0. So this entire term vanishes. So it becomes for ideal gas, we know dH is equal to Cp dt. Now, another term that might be required in physics, that is coefficient of isothermal compressibility. So that is the rate of change of volume with respect to pressure at constant temperature and number of moles, that is Boyle's law per unit volume. There. So minus, because Boyle's law, there is graph is the slope is negative. When volume increases, pressure decreases. So that is why a minus sign is there. So it is beta. And we apply the Boyle's law, PV is equal to K, and make a derivative on both the sides, dd, only dd, and so this will be pdv plus vdp, and the derivation of a constant is equal to 0, and from the interchange we get dv by dp is equal to minus v by p. Now if you apply dv by dp as minus v by p, vb get cancelled, minus minus becomes plus. So the coefficient of isothermal compressibility, temperature, isothermal means temperature remains constant, means variation with pressure. Indirectly means variation with pressure. That was variation with temperature, Charles' law. This was variation with pressure, Boyle's law. So that was 1 by T, this is 1 by P. This is an expression which is very popular in gaseous state, alpha square TV by beta, involving both coefficient of thermal expansion and coefficient of isothermal compressibility taken together. One is a square form, alpha square Tb by beta ultimately will be equal to R Cp minus Cv. I was telling that state function should be exact differential. For exact differential, the integration of the exact differential from initial state to final state will be the net change delta x. Such a thing cannot be done for this. Only for path independent functions, state functions, you can do this. dw and dq are inexact differential. So actually it is to be written as cross. They are inexact differentials, and their integration will not be written as delta w or delta q. No, simply w and q, because they are inexact differential. And I have told you that any state function, any expressed as a function of another two state functions, state variables, then this will hold good, as I have already mentioned. And the other one is Euler's reciprocity, that you can have a look, and cyclic rule also will hold good. Just del p by del v into del v by del t into del t by del p, that will be equal to -1. This is called the cyclic rule. So thus, and therefore dq and dw should be written as d cross w, d cross q, because they are not exact differential. Their integration will not give a delta, capital delta. Rather, it will be only q, only w. So these are all, uh, things which, let us now come back to today's program. This you can write down if you want. If you write down, it will be more pleasurable, and you can have a little confidence on that particular thing which we discussed today. But let us talk about, let us do a bit of, no, we will be doing a bit of revision after. We will make an extensive revision from start to finish. Be ready for that. What? Any question at this point of time?
No, sir. No, sir. No, sir.
Omkar, your microphone is opening and closing, and don't open it unless and until you are not disturbed by others.
No, sir,
Yeah.
that was not mine.
Then whose?
Sir,
Okay.
mine.
Okay. Okay. You close it. Is your revered sister is disturbing you?
No, sir.
Okay. Let us discuss today the second law for of thermodynamics for uh, refrigeration and heat pump. I think yesterday, have you written down the Carnot cycle in your copies? I have told you.
Yes,
Yes,
sir.
sir. Written, sir. Done, sir.
Samidha, I think you might have not
Yes,
got time. Have you written?
yes, sir.
What a pleasant surprise you are. Now see, we'll be talking about thermodynamics of refrigeration, heat pump, and also we discuss about the third law of thermodynamics because we are determined to finish thermodynamics today officially, but unofficially our doubts will be cleared at any time. And those who are watching, they can directly ask or communicate to me for clarifying their doubts on thermodynamics, which I have delivered on a live program basis. Well, this is just the opposite of Carnot cycle. This is called the reverse Carnot cycle, as you mentioned here, reverse Carnot cycle. What? And it is a non-spontaneous process. It can be a heat pump or it can be a refrigeration. Refrigeration has two applications. One is the household refrigerators, as we call freezes, freeze in colloquial language, freeze. We have kept tomato in the fridge, fruits in the fridge, refrigerators, and air conditioners, without which nowadays we are not able to, in hot countries like India and elsewhere, people are quite used to uh, air conditioners. So these air conditioners and refrigerators, they are in general called, the principle is refrigeration. And in colder countries like Northern America, North America, Canada, and other northern European countries as a whole, they definitely have another expression or category of the same reverse Carnot cycle, where they will get their room heated up instead of being cooled with respect to outside temperature. Instead of being cooler, it will be hotter so that you feel better. Otherwise, the outside temperature is minus or 0 or maybe 2 degree, but inside is 20 or 25, you feel better. So that is called heat pump. And when it is outside is hot and you need to, outside is 30, 37, 35, and you need 20, 25, feel good, then that is refrigeration, principle of refrigeration. But both have the same principle, reverse Carnot cycle. So in that, what is done? W amount of work is done upon the system. There, the system was doing work in Carnot cycle. It was doing, running the engine, internal combustion engine, and the car was moving right that. So here, the opposite thing will happen. and the cycle will go in anti-clockwise direction, opposite direction of what we had done in Carnot cycle. And then W amount of work is done, QC amount of heat is drawn from the cold source. Here, the source is cold, I mean at a lower temperature, that is at Tc. That is the source because that will give thermal energy. So heat will be drawn under compulsion because work is done, drawn from the cold source, and it will transfer QH amount of heat to the hot sink. Here sink is hot, the opposite. During the process, we will take the benefit. If our room will be cold source, the cold source if will be our room, then our room will be getting cold. And if the room will be the hot sink, then temperature will increase from outside source, outside surrounding, and we will be getting warmer, hotter. The only difference is which is being made as hot source, cold source, and which is made as hot sink. So you just write down, I want you to write down a little bit this sentence: when W amount of work is done, QC amount of heat is drawn, and just mention reverse Carnot cycle and write down both refrigeration and heat pump. Heat pump is almost not existent in our places. We do not know what is how the heat pump works. It does, the same machine here, even in US, does the opposite work. I mean, makes not opposite cycle, makes the room as the the hot sink, and outside as the cold source. Whenever there will be requirement of warming the room with respect to relative to outside, when we require, particularly the place where I am staying, that is southern United States, in California, Southern California, very bordering to Mexico, that is in San Diego, where there is a temperate climate. Um, Hardly the temperature in the entire year exceeds 25 degrees Celsius. 25 degrees Celsius. So what we say summer is 25 to 26, and outside is, if you go to the sun, you might be feeling little hot. The moment you come to shade, to a place where there is no sunlight, you will feel chilled. And also while you will be walking under the sun with a hat or a cap, you will feel the cold sea breeze from the Pacific Ocean will be giving you a soothing touch. Here the Americans, they don't go outside during the daytime, but we guys, we enjoy with a cap. We can walk down even under the sun and enjoy the cold breeze coming from the Pacific Ocean. So why I was saying that here we usually don't need heat pump, very rarely. It is, the provision is there. But when I was staying with with one of my sons' family in New York, where the climate is extreme, in cold it will go to sub-zero, zero, sub-zero, and there will be icing, snowing. Most of the time the road will be covered with snow. But in the summer, August, July, August, the temperature can go up to 35, 33, 34, not like us, 44, 34, 34, 35. Here, it's 25. there 35, 37, max 36. So it will be hot, really hot. They need heat pump. They need, sorry, refrigeration. But otherwise, most of the time, they use the warming condition, heat pump they require in the entire summer days when the outside temperature is 0, -5, then their room has to be, made warmer to 25 degree at least or 22 degree at least to feel good. So heat pump will be required throughout the winter there. In summer, they will be using the 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 refrigeration mode, the air conditioner mode. I mean, both air conditioning can be used for refrigeration mode and heat pump mode. Usually, air condition, we believe that it is cooling effect, but it can be also heat pump. Let's go little more, and we will complete very soon. Now see what is happening. Work is being done by us by using motor. We will be doing work. Electrical energy will be converted to mechanical energy, and we'll be doing work on some that is called refrigerant liquid. It will be a very volatile liquid, like earlier it was chlorofluorocarbons, and now substitutes are being made. So some volatile liquids will be vaporized easily. We'll be doing work on that. And here it will draw QC amount of energy will be drawn from the cold source, and it will throw QH. What I said, is it QH? Yes, QH amount of heat, the hot sink. And this heat pump, this is the principle of both refrigeration and heat pump. If the room is made as hot sink, then it is heat pump. Room heating happens. If room or inside of the refrigerator is made as cold source, from where the heat will be drawn, then it will be a cooling effect. Is the principle of air conditioning. In general, we call air conditioning or refrigeration. Cycle is same. Oh, do you want to write or you proceed? What do you want?
Sir, 1 minute, sir.
Yes, yes, for 1 minute, sir.
So the big bro, I forgot to give him the link. So he is perhaps watching in the YouTube and asking me. I'm Krishna. His name is Krishna. Okay, done.
Yes, sir.
Now,
Yes, sir.
this is the whole cycle. Here you see this is the reverse Carnot cycle operating in the opposite direction. We go from 1, this is 1, I, then 2, then 3, then 4. In 1, this is 1. Here, you see amount of heat is drawn from the cold source, and it will evaporate, the refrigerant liquid to vapor. This vapor here will be compressed by the application of W amount of work on the system by the electrical motor. W amount of W net is meaningless because there is only one work. W amount of, supposing 1500 joules of work has been input to the system, and the gas will be compressed here, and it will be since it will be expansion, this process is no, this will be compression, I'm sorry, it's a compression during, this is adiabatic process. This now, this is isothermal, I am putting in, this is isothermal expansion where it evaporates, then immediately there is adiabatic compression too. So where the temperature automatically goes from QC to QH. As and when the temperature becomes equal to QH, there is no further compression, then it is allowed to condense and goes to a isothermal expansion process. So during isothermal expansion, isothermal compression, further compression, this is adiabatic compression, this is isothermal compression. So it is condensed to a liquid here, and it throws numerically greater amount of energy, 4500 joules. I have given you for an example, it receives 300 joules, 3000 joules, and gives back to the hot sink. This is the heat sink, I call hot sink, 4500 joules. And this liquid comes again for expansion. There is a bulb plus evaporation happens. So both liquid and vapor, they enter to the evaporator, and this process is again, this is compression, this is adiabatic, adiabatic expansion. Adiabatic expansion, the temperature decreases from QH to QC, that becomes equal to the temperature of the cold source. So this is the opposite cycle that happens, and you will find that in a cyclic process, the net work done, which is writing as a net, I am not writing net because only one work is done, is equal to QC plus QH. QH is negative because it is thrown, so it is negative. So minus, so QH comes to the front, QH minus QC. So you see 4,500 minus 3,000 is equal to the amount of work done. So the principle of cyclic process is upheld, and we find less amount of work is done, and during the process more amount of energy, heat is drawn. Heat is not a true energy. Heat brings about the increase or decrease in internal energy. Heat is a mode of energy transfer, is a mode, simply a mode. So 3000 joules more heat is drawn from the cold source, still more heat is thrown to the sink, and we only invest a little quantity of work into the system. So this you can draw later, but at least you can draw this one. This is isothermal. One is isothermal expansion. Two is adiabatic compression. And three is again compression, isothermal compression. And four is adiabatic expansion. So there will be two expansion, two compressions, two isothermal process and two adiabatic process. That also you found in the Carnot cycle. This is reverse Carnot cycle. Carnot cycle is for heat engines. This is for refrigeration. Both works on second law. And you remember that in Joule-Thomson effect, which is based on first law, which is an isoenthalpic process. You know, the cyclic process is isoentropic, reversible process, but the irreversible process is not isoentropic. The reversible process is isoentropic, where the entropy change is 0 for the system and also for the surrounding. And if it is irreversible, both will have changes. The the Clausius inequality says, and we also have visualized that system loses some entropy. Del S is negative for system, and for surrounding it is greater than. The increase is more for the surrounding than the decrease of entropy of the system. So net entropy of the system increases because it is an irreversible process, a fast process. And this is adiabatic expansion, the fourth one here. So this much you do, and the rest part you can do at home. I'm so sorry, because we have to anyhow complete. We have already explained, and here you have to write. There is a term here in Carnot cycle. It was efficiency. The term was efficiency eta, but here it is coefficient of performance. If it is a principle of refrigeration cooling effect, then the coefficient of performance is QC by W, the amount of heat drawn from the cold source, that is our room or inside of the refrigerator, by the work done externally, I mean onto the system. So which is equal to QC, and we have already seen W is equal to QH minus QC. So they are proportional to their temperatures. So this is the ratio between the temperature Tc, the temperature at the cold source, divided by temperature at the hot sink minus temperature at the cold source. So they are all temperature dependent. If it is a heat pump, then the only difference will be, instead of QC, the amount of heat that is thrown to the hot sink by the same. The denominator is same, and therefore the ratio will be TH by TH minus TC, where TH is the temperature of the hot sink and TC is the temperature of the cold source. You can write down this: coefficient of performance for refrigeration, coefficient of performance for heat pump. And after that, we'll be going to a fascinating third law. Of course, very short. Second law is much bigger because entropy change is coming. And after some time, please remind me, we'll be talking of the entropy change of a entropic spring, that is a rubber band, which is opposite to the entropy change that happens in a normal metallic spring. And when egg boils, what happens to the entropy? It seems it is frozen, I mean, it is solidified, the entropy must decrease, but opposite thing happens. We'll talk about that. Some biological discussion will come to make us understand that the entropy change while boiling an egg is not what we generally lay persons just knowing about entropy will think, unless you have some idea about the biomolecules, how they have interaction between molecules. You cannot give correct answer. Have you written?
Yes, sir.
Then
Yes, yes.
yeah, I had a question. What happens if refrigerator's door is kept open in a closed room for some time? Somebody asked me, or maybe it was put in some examination, that when a refrigerator's door inside a closed room, uh, is kept open for some time, what will happen? The vicinity of that refrigerator might be giving you a cooling effect, but after some time, the entire average room temperature inside the room will be more. You will be thinking that because I have opened the room and the door of the refrigerator, my my room will be cold. Then there will be no need of a air conditioner sitting at the top or maybe somewhere fixed. If you want the cooling effect by opening the door of the refrigerator, that doesn't happen. Why? Because I've written down here the average temperature of the room will increase ultimately, although the immediate vicinity of the room of the door outside the door feels cool. This is because more heat will be drawn from the room. More heat will enter inside the fridge from the room to restore the inside temperature, because it is monitored by a thermostat. More heat will be withdrawn from it, and hence more heat will be thrown outside, because it is a closed room. Because outside is not like a air conditioner, the sink is outside, the cold source is inside and hot sink is outside. So outside temperature will increase, but the refrigerator is kept inside the room, so outside of the refrigerator is inside the room, so that will throw more heat, because the source, cold source, and the hot sink is the same room, so more heat will be thrown on the backside, and that will be dissipated throughout the room, and ultimately the room's temperature will rise after some time. Understood?
Yes, sir.
Now let us have some discussion on third law of thermodynamics. It says that, write down third law of thermodynamics, because today we'll be completing our program, because we have done a lot of advanced numericals, uh, but some graphical discussion might be needed, and you find any numerical from any source on thermodynamics, and I'm sure you can tackle them. If you not, then don't hesitate to take my help. Third law says at 0 Kelvin, absolute zero, entropy of pure and perfect crystal is zero. The entropy, absolute entropy, becomes zero. The particles, you just write down this. That is the, the particles cease to show any type of motion, neither translational, nor vibrational, nor rotational, nothing, and acquire single microstate, and will have no chaos, or randomness will be zero. So the absolute entropy will be zero. Of course, this is an ideal condition. In reality, there cannot be no 100% perfect crystal. There will be some amount of, maybe a trace of defect in the crystal, trace. And also 0 Kelvin is unattainable. Till date, they have gone close to zero, maybe of the order of 10 to the power minus 5 K, 0.0001 K, but not 0 K. It's not possible. Third law stipulates also that this is the indirect, you know, just like the velocity of light or any electromagnetic wave, 3 into 10 to the power 2.99 or 3 into 10 to the 10, is not attainable by any material particle. It will be slightly less than that, but cannot be equal to that. Very tend to C, but cannot be equal to C. That is the relativity, Einstein's relativity. So that stipulates the material particle's velocity can never ever be equal to C. Maybe 10 years before, a group of scientists from Europe, maybe Germany, Switzerland, and some group, they revolutionized. They made a great, hue and cry by saying that we have made neutrinos, not neutrons, neutrinos, you know, travel with velocity greater than the velocity of light. They had some of their papers accepted in journals, very coveted journals. So people around the world said Einstein's theory of relativity has been challenged, and people have got, they allowed neutrinos from one top of the hill to travel to another top of the hill, and they found the distance by time, the velocity is exceeding the velocity of light. So later on, after maybe few months, they withdrew their paper, and the editor gave a point of uh, distress, agony for publishing a an unconfirmed article, because the authors, they found the calculations were wrong, and their neutrinos are never ever
Sir,
traveling at a speed greater than c.
sir,
Yes,
is it neutrino or something tyon? Ty Tyon.
pion, pion, tauon, these are as you have taken my program, the at particle physics. I think you have taken the particle.
Yes, sir.
Yeah. So the main two groups, leptons and quarks. So in the lepton category, you get electron, muon, and tauon or tau. These are -1. The charge is -1. And each of these negatively charged particles, electron is the lightest particle, then little heavier is muon, and still much heavier is tauon. And all these three have the respective neutrino particles. So neutrino that we say commonly neutrino is actually electron neutrino. Neutrino is the corresponding neutral particle, and that is neutrino. It has negligible mass, but it has mass. And muon has muon neutrino, and tauon has tauon neutrino. So there are three neutrinos having no charge, and three negatively charged particles, electron, muon, and tauon. So the particles that they allowed to go from one place to the other and determine the speed is electron neutrino. Muon neutrino was little heavier. Of course, the the, the neutrinos are lighter, much lighter than their respective mother particles. Mother particles are negatively charged. So I have to confirm when you are saying that some muon term is there. It might be muon neutrino, but neutrino must be
No, sir. No, sir, not
neutral.
muon. Sir, it is tyon. Tyon.
Ion, what is tyon? That is nothing I know about tyon. It is tauon.
Yeah,
Tau.
yes, sir.
Tauon is a very heavy particle. I have to confirm if they send a negatively charged particle tauon, which is much heavier. It is almost, the size. I mean, the size, the mass of a proton. The tauon is very heavy. If you look to the literature, the mass, how much giga electron volt, it will be in terms of zev by c square. So 1 zev by c square is proton, and I think a tower is such a heavy particle. I doubt. I will check, right? But
Okay,
I
sir.
was
Yes.
I was 101% sure that some neutrino particles were involved in that kind of research. I can't say fake research. They did a lot of work to prove that we can our the particle the particle speed can exceed the velocity of light, the electromagnetic waves, but that failed actually. So in the similar manner, the 0k is unattainable. However, for highly crystalline substance, we presume that at absolute zero, near absolute zero, at or near absolute zero, the entropy change of any process tends to zero when T tends to zero. Hence, the absolute entropy must be going to zero. So that was the proposition, that when all molecular motions, atomic motions cease, the entropy of that particular substance, uh, all substance must be in their solid state. Um, but for which are amorphous solids, their entropies are not zero at absolute zero. Entropy is calculated at other temperatures taking S0 is equal to 0 are called third law entropies. The table that we were using to find del S in our numericals, those tables are third law entropies. The absolute entropies of any substance at the standard state, say 25 degrees Celsius, has been determined from the third law, taking 0 as its entropy at absolute 0, and then you can calculate what will happen till it goes from absolute 0, then it will go in the solid state to its melting point, absorbing Cp del T, you know delta T amount of heat, and then you have to integrate. Of course, the temperature is varying. You have to integrate that. I will tell you. And then at the fusion temperature or the melting temperature, it will be absorbing the molar heat of fusion. Temperature will remain static. And then again, from the melting point to 25 degrees Celsius, or if you go to its boiling point, again you have to go, a liquid state Cp is different from the solid state Cp. You have to take that into account. And then at the boiling point, you will have the molar heat of vaporization. Will be doing that. Temperature will remain constant, and find what is the entropy change. Entropy change will have to be integration, because if you are going over a range of temperature, then dq by T, not dt, it's not T, and of course Cp will be there, then you have to integrate. So I will show you how you do. Have you written down something?
Yes, sir.
Yes, sir.
Yes, sir.
Wow. So for amorphous substances like glass, there is residual entropy even near 0 Kelvin. So those are not considered for finding the absolute entropies of at other temperatures. So you will not find the entropy of absolute entropy of glass at 25 degree. The data will not be correct. Consequence of third law, it is impossible by any procedure, no matter how idealized, to reduce the temperature of any closed system to 0 Kelvin in any finite number of finite operations, any finite number of operations. So 0 Kelvin is unattainable. You can go up to 10 to the minus 5 K, 0.000, 4 zeros and 1 K, but not 0 K. So here we shall be calculating, supposing you are asked to find out the absolute entropy at some temperature above its boiling point. Just for a case of calculation we are doing, but we will be staying somewhere at 25 degree. The data given in the table are standard state, but supposing we will be going till supposing water or any other, in fact, solid, which is a solid. Absolute 0 is a perfect crystal. So this is 0. The S0 will be taken as 0. This will be taken as 0. And then from 0 to up to the freezing point, it will be Cp dt. That is Q. Q is nothing but dq. Or now we can put a cross sign. It's not a perfect differential. So dq by T is the entropy change, ds, small ds. And we have to integrate over the entire period from 0 to till we reach the freezing point. So we know then this ln Cp will come outside. It will be ln T2 by T1. We know ln T2 by T1. We know this. And then under constant fusion temperature or melting point, as we say, you have to the heat change by temperature, constant temperature. This is equilibrium stage where both the solid and liquid remain in equilibrium. So del G naught will be equal to 0. So in that case, we write del H, this molar heat of fusion by the freezing point. we call the the melting point of that solid. And then after complete melting, we go from the melting point till the boiling point. So TF to TB again, the Cp of liquid will be taken. This is Cp of solid. Cp of liquid is little different. We've taken into dt by t and take the integration to find the entire change of delta, capital delta S from TF, that is freezing point, actually it should be called melting point, to the boiling point. Then at the boiling, you have the equilibrium condition. This integration will not be happening because temperature is not changing. So del H vaporization, molar heat of vaporization by TB. And then finally, when you go to above boiling point, when it is a vapor, you are not staying at its boiling point, going above its boiling point. Then you have to take Cp of gas, which is completely different from the Cp of liquids and solids, and do the same thing till you attain your desired temperature. So you can write down this. You can write down how to calculate the absolute entropy at a given temperature. Supposing you are asked, you can calculate, because this will be Cp will come outside, then dt by t, 1 by t dt is ln t. So it is ln Tf, because ln 0 will be equal to 1, so it will be ln Tf. This will be 0. But here there will be T2 by T1, that is Tb by Tf will be there, that's term will be there. And here also it will be T by Tb there. But here the ln that term will vanish, it will be simply ln Tf. And interestingly, up to 16 Kelvin, up to 16 K, the entropy of most solids which are non-metallic is calculated from the following relation. St up to 16 is Cp by 3, because all these in up to 16 will be almost in the solid state. So why? Because at those temperature, Cp is taken as Tq with a constant A. This is not the van der Waals constant, a constant A, Tq. So when you integrate Cp dt by t from 0 to 16, then you will find a Tq by t, 1t cancels and becomes t square. Then it again become a Tq by 3. So again a Tq, you will be taking Cp, so Cp by 3, ultimately you take Cp by 3. That integration is replaced by, from 0 to 16 is replaced by Cp by 3. That is most solids which are non-metallic like sulfur, phosphorus and all other. Oxygen, maybe 16 Kelvin, up to 0 to 16 Kelvin, oxygen is a solid. Hydrogen is not a solid perhaps, but oxygen, nitrogen, they are solid. Minus 100, minus 186, minus 196 are there, freezing points. So you can check. Now for most metallic solids near 0 K, so some other equation is used, not Cp by 3, it is Cp for metals. And here I have shown you a calculation, a real calculation. The calculation has not been done. So find the absolute entropy of water liquid at 25 degree, not go above its boiling point, up to 25 degree. So we start from S0, which is 0. Then Cp by T, we have to take it, since it is non-metallic, we have to take it as Cp by 3. So Cp by 3 we might have used. Then we have to integrate here 16 to, this is ln 273 by 16. Ln 273 by 16 we calculate. And then this is molar heat of fusion by the fusion temperature of ice, that is 273. We have come to the fusion point. Then we go from 0 degree Celsius to 25 degree 298. Then you have to make Cp ln 298 by 273, and we got a value of 70 joules per Kelvin per mole of water. At lower temperature region, each term is determined from the area bound by the graph of Cp by T versus T. I have shown here this Cp by T. If you have a graph somewhere given, then the integration will be integral value will be the area bound by that curve, that you know. So if the Cp by T versus T graph is given, then the area bound by the graph is that. So this is the liquid state, this is the gaseous phase, you can add the areas. But during a constant temperature, you have to calculate this thing, you have to calculate this part. That is not area bound by the graph. There is no integration here. But for changing temperature, you can, if you have the graph, take the area bound by the graph, that will be the change in entropy, Cp by T versus T. And these are the absolute entropies, we call third law entropies, and we have done several problems where we find the entropy change during a reaction, right minus left. Molar entropies data are given, so you have to multiply the coefficients. Zeroth law is very interesting. The shortest law ever possible. If two systems are in thermal equilibrium to a third system, supposing A and B are independently in equilibrium with a third system C, then A and B are also in thermal equilibrium. This is understood. And all the three will be at the same temperature, there will be no heat flow. This law tells about the direction of heat flow. So only when there is a high temperature to low temperature, then heat will flow from high temperature to low temperature, Q. If very, very slowly, infinitesimally slowly, it is a reversible process. If it's sudden passage of heat, then it will be irreversible. But if the opposite will happen, then you have to do work. Second law also has done that you can also extract heat from a cold body at a lower temperature and throw. You have to throw. You can draw by applying work, but not all work that you do onto the system will be used for drawing heat, and not rejecting a part of it, not a part, some heat. We saw that the amount of heat thrown to the hot sink is greater than the amount of heat that is withdrawn from the cold source. So that finishes our program. But we'll talk about the spring. Have you written down zeroth law?
Sir, one
First
minute,
part,
sir.
just the
Yes,
first part, just to remain to have that in your copy. It's nothing. Zeroth law is not a big law, and you never get a question from that. But still, we have to cover everything, every aspect of thermodynamics. Of course, in your program, there is no statistical thermodynamics, which hits upon the individual molecules, atoms, and have a probability. So that is taught to higher level students. That is called statistical thermodynamics. These are thermodynamics in bulk. The bulk matter is considered for our study, not the individual molecules, atoms.
yes, sir, done.
Yes, sir.
So what happens to a now let me revise and see what is being left. See, this is the open, closed, and isolated system. Dithermic wall, conducting wall, and adiabatic wall. Extensive property, intensive property. State, variable state function, and which are not state functions, Q and W. Internal energy, which is a function of temperature only, is directly proportional to temperature. And we know that the internal energy of a isolated system or universe will remain constant. Whatever one will lose, the other one will gain. So there is a conservation of energy. And to be more specific, at that time when heat and work were the two things needed for the internal combustion engine, change in internal energy is the sum of, as we say, the Indian INR and American dollar, where W is minus P delta V, we say. The work done on the system is positive, by the system is negative, but in physics it is the opposite. And they say del U is equal to Q minus W. They say del U is equal to Q minus W, and the sign conventions are opposite. So that we have done. And in the first law, we have another definition. It is impossible to have a perpetual motion machine of the first kind. It is the first law, so it is first kind. A machine cannot run indefinitely or do work on the surrounding indefinitely without drawing equivalent amount of heat, energy, heat. Energy is a misnomer, heat from the external source. That means there is always a equivalence between heat and work. Both change the internal energy, and there is always a conservation of energy. In human metabolism is the conversion of food into heat transfer, work, and if you take more food and do not do work, physical exercise, mental exercise, physical exercise, and the those which are digested but not converted into work, they will be stored as fat, and you will be gaining unnecessary weight. It's not that you are in a growing stage, you will grow in 3 dimension, but you will grow in 1 dimension. Maybe you have a bulky tummy, and maybe some people they grow uniformly, length, breadth, not height, length, breadth together. uh, 3 dimension means it must be the third dimension, but not the height in the usual sense I'm talking. So metabolism is an interesting example of the first law of thermodynamics, where energy is conserved. These problems you have done first law problem, and if it is in thermodynamic equilibrium, we mean all the 3 equilibria have been attained. Mechanical, no unbalanced force is acting. Thermal equilibrium, no heat transfer. And chemical equilibrium, no progress of reaction, has come to equilibrium stage. Irreversible and reversible processes we already know, and work done in irreversible process. This is, interestingly, I was just thinking of, I will be, don't write down, or you can write down. We were talking of comparing between the, not this one, I'm so sorry. So when you have time and you think about it, you will be really, this is expansion I am talking of, PV graph, and this is what? Which process? We are carrying out expansion.
Isobaric, sir.
Isobaric.
Isobaric
Yes, right.
expansion.
So can you tell me how it happens? It's not that it is not equal to or equivalent to that we have a 20 kg load and we removed, that means it was under high pressure inside, and something happened, the pressure suddenly decreased to 1 atmosphere, then sudden expansion happens. That is different. There temperature doesn't change. It is almost like a adiabatic process, and immediately there will be a loss of heat, a loss of internal energy, and there will be equilibrium, thermal equilibrium, because it is a dithermic wall. So will happen, I mean thermal equilibrium will attain. This is not different. You are expanding due to increase in temperature. You are raising the temperature, therefore volume is increasing. That is isobaric process. There, when some gaseous system was under high pressure, and suddenly maybe during a chemical reaction pressure decreased, or externally we removed the 20 kg load and put at 1 kg load, somehow the pressure decreased and it suddenly expanded. It is something, it is the final pressure to which it will expand, that this this is the final pressure under which it will expand. So this area will be the work done. That is different from what we are now doing in isobaric process, that starting point is same. Under same pressure condition, all the three processes will begin, while for isobaric pressure will remain constant. Supposing the atmosphere is there, continuously it is a movable piston. Atmosphere pressure is always there, closed system, but movable piston. And you are raising the temperature. You have used a Bunsen burner and you are raising the temperature slowly, automatically the piston level will be risen up and up. This is isobaric expansion. You are raising the temperature. There you are not raising the temperature or decreasing the temperature. There, therefore, sudden processes, even in a dithermic wall, they are taken to be a quasi-adiabatic process. Immediately, when there is expansion, the heat is reduced. I mean, the temperature is reduced. But since adiabatic wall is there, outside there is a heat flow from outside, and temperature remains constant after some time. But here is something different. So, isobaric work done is greater than this is what? Second one?
Sir, isothermal.
Isothermal. And the third one is?
Adiabatic.
Adiabatic.
I am not showing the isochoric process. There is no work done. I am not showing. Let me remove it. But if you are carrying out isochoric, you call it isochoric cooling, because pressure is decreasing only because you are reducing the temperature. Reducing the temperature is the cause, and the effect is reduction in pressure, not the opposite. You can't reduce the pressure and then you experience there is a reduction in temperature. No, because the volume is kept fixed, you are kept in a closed and sealed container, and you are decreasing the temperature, the pressure is decreasing, the kinetic energy of the molecules is decreasing, so the force with which it is hitting on the walls is decreasing, so also the pressure. So uh, this is expansion. And you know why the adiabatic curve is lying below the isothermal curve during expansion? It is because there is, in expansion, there is a cooling effect. So the corresponding, at any fixed volume, the corresponding pressure is less. As the temperature is less, pressure is less, Hamilton's law. Or at any constant pressure, if the temperature is less, the volume is also less, Charles' law. So the expansion graph for the adiabatic process will remain below the expansion graph for the isothermal process. But if you start the compression process, as we discussed, from same pressure point, and you are going in this, one graph is this and the one graph is this. Now see, what is this graph? You are coming to the same volume, for example, some V1, this is V initial to V final, this is lower. So what is this process?
Sir, isobaric.
Isobaric, and that will be doing the least work, because we started from a lower pressure and pressure remains constant. So we have also reduced the temperature, we have cooled down progressively, so that volume has decreased, because the piston, movable piston is there, pressure will be always 1 atmosphere. Because the temperature is reduced, volume is reduced. So that situation is completely different from when you compress by suddenly removing the 1 kg load and applying 10-20 kg load. It has been compressed under 20 kg program and not under 1 kg program. That is different, where the heat is generated immediately because it is to be treated as a quasi adiabatic process. But it is, since that is a dithermic wall, then the thermal equilibrium will be attained within short time. But here you are reducing the temperature so that you are carrying out the compression process. You are carrying out the volume reduction because you are reducing the temperature, pressure remaining constant. And what is the next graph? This is
Sir,
isobaric.
isothermal.
And this is isothermal.
Isothermal.
And the highest, I mean the uppermost graph is
Adiabatic.
Adiabatic. Because in adiabatic compression, the temperature is increased. So at a fixed pressure, the volume will be more for adiabatic because temperature is increased. More the temperature, more the volume. And at fixed volume, the pressure will be more for adiabatic, Hamilton's law. So what I was looking to, these things you know, and therefore during a irreversible compression, even removing 1 kg load and applying 20 kg load, the work done will be more because it will be compressing under 20 kg, not 1 kg, which you will not find in most of the sources. This you already know, we have done many problems. Then the introduction of the enthalpy, which is also called heat content, where PV energy comes into picture because the heat absorbed or evolved at constant pressure was found to be different from the heat absorbed or evolved at constant volume. A part of the heat was used for compression work or expansion work. So that gave rise to another thermodynamic variable called enthalpy. The heat absorbed or evolved at then chemical process, it is equal to delta N RT. You all these things you know, and we have calculated nothing. And isothermal process, adiabatic process, all these things you know, isochoric process, isobaric process, cyclic process, expansion in vacuum, and this graph. And let me put this graph now for the benefit of others. PV graph, this is particularly expansion. I have written expansion, but compression will be from this point the same volume, for example, V initial to V final. This is the compression graph. This will be adiabatic. This will be isothermal. This will be isobaric. This you know. Yeah. This Mr. Rudra, you were seeking interested, but I don't find any question coming from the real gas. If you find,
Sir,
let me.
sir, I have one, sir.
Yeah, you tell me. Let me know. Let me know, and we will
So now,
discuss. No,
so
not
now.
now. Not
Okay,
now.
sir.
You send me. We will be discussing all your doubts in a separate class. Maybe if the doubts are interesting, then I will make it public. If they are little easy type, then I will restrict our discussion with you. Uh, of course, you in plural. Now, this is the van der Waals equation, and when we integrate from volume V1 to V2, we get this value. So, work done for isothermal reversible process for a real gas is not RT ln V2 by V1. It is RT ln V2 minus B by V1 minus V plus the van der Waals constant A 1 by V2 minus 1 by V1. This you have to use for finding out the work done for any real gas for which A and B data, the van der Waals constants data are given. You have to use this equation. And any other related things we can discuss later. Not today, we'll wind up. This we have already done. This heat capacities, they are obtained, uh, this is the lower graph is internal energy, the higher graph is H, this is E. So dH by dt, the slope will give you the Cp, and dE by dt will give you Cv. So the slope of this line of U versus T and H versus T will give you the Cp, which is variable for liquid then when phase transition occur, it goes like this, and when the phase transition, it remains straight, and then it takes this slope slightly different. Slope is different. Therefore, you have to have the Cp or Cv values, even if it is a solid or liquid. There is only one molar heat capacity, that is at constant pressure. There is no two heat capacities for liquids and solids, because pressure only is pertaining to gas. I mean, the atmospheric pressure is remaining constant over the liquid and solid whose heat capacities you are wanting. So I am showing, and we have discussed also, how the equipartition theorem will tell you for each degree of freedom half nRT, and then there are how many 3 translational degrees of freedom, and 2 rotational freedom for diatomics, 3 for polyatomics, and the number of vibrational degrees of freedom is 3n minus 5 for non linear, and 3n minus 6 for non-linear, and each has a pair potential and vibrational counterpart. So vibrational energy levels are not at all considered, because at ordinary conditions those vibrational levels are not excited, they remain in the ground state. So we don't consider the degree of freedom increases from translational 3 is must, and rotational sometimes 2 5 by 2, and 3 3 plus 3 6 by 2. And sometimes if vibrational will come, then we have to take. Sometimes in diatomics, vibrational, one vibrational, that in fact 2, potential and kinetic 2. So 2 are added, sometimes 7 by 2 comes at a very high temperature for diatomics. That I have already discussed and I have given you. This is not required. I have written also. I will send this file too. If at all I have left something, you will find. This we have done, these adiabatic processes, and there is another equation which I have asked not to use. You can use adiabatic work done by using this expression after integration. We have found it, but I always say for adiabatic irreversible process, you equate the two, n Cv delta T is equal to minus P external into delta V, find the final temperature, and then find Cv delta T to find delta U, which is equal to W. But for this is for reversible, you use V1 T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 1 adiabatic gas laws to find the final temperature. During expansion, the final temperature in reversible process is lower than that of the irreversible process. During compression, the irreversible process will be having higher temperature than the reversible process, because the work done will be greater, because it is area under a big rectangle. So that you know. So therefore I have, so these are the revision at a glance, all these values, I mean all these expressions that we use for solving problems, which you know, and these are the problems which most of which we have done. This we have also done. These are all very, now it will be looking very simple. First law, this entropy, then second law we are entering into and this is a funny slide, that in this room this girl is studying, the entropy of the room is less, because all these are in ordered state. But now after few days, after her mom ordered the room, because therefore I funnily and in a lighter vein say to my students, go to your house and say to your mommy and daddy, I will be erratic and I'll do something weird. Why? Because second law says that the entropy of everything will increase in a spontaneous process. So I'm a natural person, so I will be behaving weird or doing something weird because my entropy has to increase. Do something nuisance because entropy will increase. So therefore the girl naturally has done this thing, and after a few days her mom discovered that the entropy of the room has risen. This is a natural process. So you do the same thing, go back your home and spread everything whatever you have in a random manner in your room and say to your mom, this is second law. This is a natural process. Same thing. See, the guy who is staying here must be a girl, I think. I don't know. And this thing in an equilibrium stage, when del G is equal to 0, then you find entropy change. And there are several examples. Second law, and we have expressed in terms of entropy change of the universe. Then we have come back to express another term, free energy, Gibbs energy for the system, completely sidelining the surrounding. We discuss the spontaneity of a process from the Gibbs free energy. If it is negative, then it is spontaneous. And from that, we can find equilibrium constant from the famous relation del G naught is equal to minus RT ln Kp. So these things we have done. Now, if thermodynamics say no, it means yes, it means no. If it says yes, it means it may be. If kinetics may make the reaction so slow that it may not happen at all during any course of your, in your life span. So you have to optimize the temperature, even if you have to sacrifice the yield to some extent. So this we have already discussed. All these types of sums we have done. Second law, entropy changes for different systems we have done, and mixing we have done. These things we have already done. Uh, these problems are now trivial for us. Yes, stretching of a rubber band. When you stretch, the entropy decreases. Why? Because in a rubber band, those we teach to the polymer in polymer chemistry to class 12. Nowadays that course has been deleted. Very surprising. But I used to teach in rubber. Rubber band is made up of polymer. Polymers, they are long chain molecules, and in rubber, these are all in a very coiled, entangled conformation. One is coiling the other, entangling the other. They are in a coiled, heavily coiled conformation. Therefore, they are elastic. When you stretch it, the coils will uncoil. They will be elongated. So once they will be elongated, the van der Waals force of attraction, their surface area, contact area will be more, and their interaction will be more. It is an exothermic process. Heat will be, suddenly you expand and hold it, you will find a heating process, exothermic process, because the intermolecular attraction will increase and the van der Waals forces will be more energy will be released. So it will be exothermic process, and it will be going from a more disorder, more entropy to less entropy. So there will be decrease in entropy. Del S will be negative when we stretch a rubber band. That is why it is called entropic spring. But when we stretch a metallic spring, then the entropy increases. It was in a more orderly state, and it is now in a more disorderly state. Entropy increases, but it is the opposite. Exothermic and non-spontaneous, we have to do it. When you unstretch, if you leave it, then opposite will happen. The coiled conformation, sorry, and this when you stretch it, it will become uncoiled. I'm showing it, what happens. It will be straightened. It will be straightened. So they will be coming close to each other, and the van der Waals forces will be more energy will be released. So entropy del S is negative. And also del H is negative. There is the exothermic process. We'll be talking more about del H in our thermochemistry program. There will be a lot of interesting calculations, tricks for the thermochemical calculations. We'll be involving only del H. No del S, no del G, nothing. Only del H. No del U, only del H. Therefore, rubber bands are called. And when you do the opposite, I have shown here in this diagram, when you do the opposite, that is on stretching, then the more straightened conformation will go to a coiled conformation. The randomness will increase, the entropy will increase. So del S is positive during on stretching, and during stretching del S is negative. And uh, mm, just you write down, during stretching of a rubber band, del S is negative, and on stretching del S is positive. And del S is negative, del H is also negative, it is exothermic. During on stretching contraction, del H is positive, heat will be released. As the more interactive forces will be lost, the interactive forces will be killed, so heat will be absorbed from the surrounding, so it will be an endothermic process. The surrounding gets cooled, it will be having a cooling effect. Once a stressed rubber band coming to equilibrium, thermal equilibrium, immediately it will be hot, but leave it for some time and then release your stretch, you will find there is a cooling effect because the surrounding gets cooled. So have you written down, guys?
Yes, sir.
Sir.
Then this we also have discussed Carnot cycle. This is very simple, and the cyclic process, in cyclic process we have seen what happens to net entropy change. This we have done. These problems are very simple, you can do this. These problems, some of them we have done. Yes, this we have done, this we have done. This now we will be discussing the problem which Mr. Rudra has given. So I think this we have discussed, right?
Yes, sir.
I just draw
Yes,
the
sir.
TV graph. Have you drawn that yesterday?
Yes, sir.
Yes,
This
sir.
is this is not PV graph. This is TV graph, where we can depict different processes like exothermal and adiabatic. Now coming to this question, which I had sent you the answer in which file, let us straight away go to that file without wasting time. Which file I have given you?
Sir, it was there, but
Thermodynamics of equilibrium? No. In which file I have given you the answer? In our OneNote file? Now this we have done today. I will send today. 32. No. In some file, in this file, thermodynamics of equilibrium. Tell me which file. Gibbs free energy?
sir, sir, yes, sir.
Huh?
Sir, the file of Carnot cycle, you have given in the file of
Yes, sir.
Carnot cycle.
Which not send in the
Yeah,
group that cannot
Carnot
Carnot
cycle
cycle.
period.
cycle. Yeah, in Carnot cycle file, I have given you the answer. Yes, this one, right?
Yes, sir, yes, sir.
Yeah. Now, let me explain to you. Are you able to see properly, or we shall be taking this to a little OneNote and expand it a little more so that you can have a better view? Still, we can expand. Are you able to see properly?
Yes, sir, yes, sir.
Yes, sir.
Okay. Now, let us consider AB process. AB, what is AB? This is a VT graph.
Sir, isotherm.
Isothermal, because temperature is remaining constant. So AB is isothermal process. So we have found out WAB is equal to minus NR T1 constant temperature is T1 ln V2 by V1. This is V2, this is V1. This is compression. This is isothermal compression. You are reducing the volume, the pressure is volume, definitely you are decreasing, so the pressure must have increased. The Boyle's law is being followed, isothermal. So pressure must have increased to P1 to P2. P2 is a greater pressure, no doubt. P2 is greater than. Okay, so option A is wrong. Option A says in this WAB is equal to P2 into V2 minus V1 is talking about the irreversible work done. That is a constant pressure. There is no constant pressure here.
Yes, sir.
That means irreversible work done at the higher pressure. That also is incorrect. It should have been minus. Minus sign is missing and it is given irreversible. But this is reversible. If it is isothermal, it has to be reversible, and the isothermal process, the 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 relation for work done is this. So the option A, let us not forget this, let us forget about this part. If this is wrong, means this is wrong, right? Then we talk about AC. AC. AC is which process? AC.
Sir, isochoric.
Isochoric, because volume remains constant. This is isothermal, because this V1 remains constant. So when the temperature is increasing means, pressure is definitely increasing. So P2 must be greater than P1. We have already seen P2 is greater than P1 in the previous isothermal process, AB. In AC, the same P2 has come. So same pressure that the isothermal process attained, and here this is the isochoric process has also the same pressure P2. Now, in the isochoric process, Q that has been absorbed during this change of temperature is equal to del UAC, because work done is 0, NCV T2 minus T1. So, to find, this is del U. To find what is del HC, del HSE is del U plus P del V, that is NR delta T, because temperature is changing means del V we will be writing as in place of del V we write del T, because the volume is remaining constant. So this is also equal to NCP dt delta T. Del U plus NR delta T will be equal to NCP delta T, right? So let us keep it as such, go for isobaric. Here there is no such thing where delta H AC is given, delta H AC is given here. Delta H AC is equal to what? We have not yet found out. Delta H AC is equal to, whether it is equal to QBC, we have not found out. We have not done BC process. So let us go to the BC process. What is BC process?
It is isobaric.
Because
Isobaric, sir.
P2 is remaining constant, it is isobaric process. So for isobaric process, the heat absorbed evolved is equal to del UBC plus NR delta T. So T2 minus T1. So which is equal to delta HS, because you see this expression NCP delta T, NCP delta T. So del H AC is same as del H BC or QBC. So QBC is equal to del H AC, because the expression of del H AC is same as, ultimately same as it is for QBC. So this is correct. Let us see if this is correct or not. Then only we can say D, option D is also correct. Now, WBC in the isobaric process, it is the external pressure P2 or the constant pressure P2, not external, I'm sorry, the constant pressure P2 under which work is done minus P2. The final volume is V1, and the initial volume is the final volume is
Final.
BC. We are going for BC deliberately. We are
So
not going
final
in a
volume is
no
V1
no
and
we are not
initial.
no listen. We have AB. We have seen AB. We have seen AC. We are not going in a cyclic process. As per the requirement of the question, we are going AC. We are going AB. Here is AB, and now going BC, not CB. We are not following a cycle. You understand?
Yes, sir.
So WBC is equal to P2 minus P2 into final volume is V1, initial volume is V2, V1 minus V2. So bringing minus to the middle, so it will be P2, V2 minus V1. So WBC is equal to P2 into V2 minus V1. This is correct. And
Yes, sir.
QBC is equal to QBC is equal to del HAC. This is also correct. So this option B is correct now. Got it?
Yes, sir.
Okay. Then coming to delta U, because in the other option delta U is given. So delta U BC is here is given is equal to what? BC, not CB. BC is equal to NCB into final temperature T2 minus initial temperature T1. That is BC, right? So
Yes, sir.
and then coming to CA, here one CA is given. This is a very critical question. AC is given in some cases and CA is also given. In CA, coming from C to A, delta U, delta HCA is NCP T1 minus T2. T1 is the final temperature, T2 is the initial temperature. This is delta HCA is equal to NCP T1 minus T2, which is equal to delta UCA plus NR delta T. NR delta T is equal to that is equal to this is for this NCB T1 minus T2, and NR this is delta T is T1 minus T2, not T2 minus T1, because here T1 minus T2, here also T1 minus T2. So if you compare between since T1 is less than T2, we know T1 is less than T2. Yes or no?
Yes, sir.
Because this is volume is sorry, temperature is increasing here, this temperature scale. So T1 is less than T2 or T2 is greater than T1. T1 is less than T2. So del HCA is negative. So T1 is less than T2. So this T1 is less than T2. So del HCA is negative. And del UCA, where is del UCA? Del UCA, good. Del UCA is also negative because this much is del UCA and this much is del HCA. So both are negative. And also NR delta T is negative. This NRT delta T is negative. So if you take the negative sign into consideration, so this is more negative. Del HCA is more negative than del UCA. Yes or no?
Yes, sir. Yes, sir.
So del HCA is mathematically less than del UCA, not numerically, mathematically, taking minus into sign. So, and also QAC is equal to delta UBC. What is QAC? QAC already done. QAC is equal to delta UBC. Where is delta UBC? Delta U.
Sir, here NCB T2 minus T1.
Delta UBC is equal to NCB T2 minus T1, right? So
Yes, sir.
QAC is equal to NCB T2 minus T1. So QAC is equal to delta UBC, and hence the option C is correct. Delta HCA is less than delta UCA, and QAC is equal to delta UBC. So C option is also correct. Got it? Is very, very,
Yes, sir. Clear, sir.
intriguing and interesting, right?
Yes, sir.
And during the boiling of an egg, so that is still uh, not discussed. This equation you write down. This is called Kirchhoff's equation. Just write down that the change, if you have a narrow temperature range, then del H remains constant. But if the temperature is widely different, then enthalpy change also are different. Enthalpy changes are also different. So that is found from Kirchhoff's equation. Del S T2 minus del S T1 by delta T is equal to change in their Cp values. And similarly, del U T2 by minus del U T1 by delta T is change in their Cv values. So at home you write down. So this is Clausius-Clapeyron equation that we'll be doing in our class 12 program. This is regarding vapor pressure. So you forget about it now. The vapor pressure also varies with temperature. And how to find the vapor pressure of a liquid at a different temperature when the vapor pressure of the same liquid is given at a other lower temperature. So this is the expression similar to that we found in log Kp2 by Kp1 is equal to what? Del H, that is the enthalpy of the reaction, by R by 2.303, or here if it is ln, then only R into 1 by T1 minus 1 by T2. This is a similar type. There it will be equilibrium constant Kp2 by Kp1, and this is del H of the reaction. So similar type. So I gave, but this will be required in your class 12 program, the Clausius-Clapeyron equation, not in thermodynamics. And this we have already discussed. The only thing that I have to say is, yes, that in egg, what happens to egg? During, just write down, during boiling of an egg, the egg contains proteins. Proteins has many secondary structures. This proteins is also a long chain molecule, which are also twisted and which are folded. So they have the hydrogen bonding between the chains, intramolecular and intermolecular hydrogen bonding. These are called secondary, and there are also tertiary structures. So that makes the egg in their native state, which is liquid inside, having less entropy. The order is less. But once you boil it, these are secondary structures, liquid, egg. But once you boil it, the secondary structures will be broken. So these will be set free and they will entangle each other. So it will be more disorder. The secondary structure lost. The secondary structure is lost, which were binding them. Intermolecular attraction was there, so they were in more order, less disorder. Now they are set free, the order will be less, the disorder will be more, so more disorder. So del S is positive. Contrary to what we think, that boiling of an egg will decrease the entropy because it goes to the solid state. Even if it is solid, inside the solid, what we eat, that will have these protein molecules, the polypeptide chains will be devoid of their secondary structure. I think we close today's session, and thank you very much for giving me. Oh, no. We have to go for thermochemistry. That is also interesting. So this week there will be no class. So we'll be resuming on Monday, right? And during
Yes,
Yes,
that
sir.
time, Om, Saminani, and Rudra, put me your doubts, that graphical doubts, as well as the Van der Waals equation doubt that you have, or any other doubt you send me. I will.
sir. Sir, I have one doubt in assignments. Okay. We have given, sir.
Okay. Which one?
Sir, in the file Thermodynamics of Equilibrium, the SAQ2.
Okay. Let me find the file.
Yes, sir. This one, sir.
Well, yes. So, Rudra, I want to know, when you taught me how to snip from your own system without downloading the snipping tool from internet source. There are some free sources. You taught me. I think you already have acquainted yourself with the uh, Excel software
Yes, sir. Not
to
very
some
much.
extent. How to
Yes, sir.
draw the line graph, the pie graph, the bar diagram using the data in the Excel spreadsheet, and then
Yes,
find
sir.
the graph, and then find the linear equation for that linear graph, and the r square term, which is statistical term. The r square term should be very close to 1, then it is a good graph. 0.9999 will be better. And if really the points are conforming to a line, then r square will be close to 1. Have you done that?
No, sir, not that much.
So I will tell you that here the equilibrium constants for conversion of 3-phosphoglycerate. Forget about that. This is an isomeric change. One isomer changing it to another isomer. 3 isomer is giving to 2 isomer at 4 temperature. This not 4 are given the following table. At 4 temperature, yeah. What is the table?
Sir, so yes, sir.
Table is missing. Okay. Table is missing. And that is why you could not do. Draw a graph of ln k by 1 by t. Oh, I'm so sorry. I have not given the table. Oh, I'm so sorry. I will give you the table. You can draw. You can k equilibrium constants and t are given. So you make another column, find a ln k, and another column 1 by t. Then take a line graph and find the graph, the linear equation. The slope can be known. Slope and del z. Sorry. Ln Kp is equal to del S by R minus del H by RT. Yes or no? That is the fundamental equation. You remember?
Yes, sir. Yes, sir.
Yes.
Yes, sir.
So a graph of ln Kp versus 1 by t will give you say a negative slope for endothermic reaction and positive slope for exothermic reaction, supposing it is endothermic, and the slope will give you the del H by R. From the slope, you can find out del H by R. R is known, so enthalpy change can be found out. And from the intercept, in this case, you will find a negative intercept. So there will be change. So intercept is del S by R. Yes or no? From which you can find the entropy change. From the intercept, you can find the entropy change, and from the slope. And that you can know from the linear equation that the Excel software will give you. I have done this. I'm showing you. You can just take the you can take down the data, copy that in your, you guys, my family members, they are really surprised that how your students are sustaining. That day we continued for 4 hours. Now, how your students are continuing for 4 hours? They are unable to think. They are unable to, visualize that, reconcile to that. Now see, these are the data. Write down. These are the data, the equilibrium constant. These are the only 2 data given. 0, 25 degrees is asking. So I found out from the graph. From the graph, I have found out. But from the graph, I found out later. This you don't write. Only write 0. These are all Celsius. 0, 0.1535, 20.1558, 30.1569, 45.1584. So since this is the increasing, so definitely it is endothermic or exothermic. Tell me, with increase in temperature, the equilibrium constant is increasing. So is it endothermic or exothermic? We have discussed that.
Sir, endothermic.
Precisely. Ln K2 by K1 is equal to del H by R. Ln K2 by K1 is equal to del H by R 1 by T1 minus 1 by T2. 1 by T1 is always greater than T2. So this 1 by T1 minus 1 by T2 is a positive quantity. So del H, if del H is positive, then K2, which is in the numerator, will be greater. So only, and when del H is negative, the opposite thing will happen. The equilibrium constant will decrease with increase in temperature. So we are talking of an endothermic process where you find the data, a data chatta niyo, a temperature Celsius re data chatta niyo. I have done, converted to Kelvin first, then 1 by T I would column kali. Equilibrium ka ln kali taku minus re baharla. Then mu kali kono mane yere graph kali माने आकु सिलेक्ट करी इनसर्ट को गली इनसर्ट को जाई करी मु गली एठी डाटा एठी लाइन चार्ट को गली गरी करी से ऑटोमेटिकली दे देला पर ताकु पचारली इक्वेशन से इक्वेशन दे देला y is equal to -60.639x minus 1.653 and r square is a important thing to see whether the lines these points experimental points they really conform to a real straight line kete deviation kete. If r square term is nearly 1, then your data is very very good and your straight line and देखा जाउची straight line किंतु जदि न होई थांता गोटे पॉइंट एपटे थांता गोटे पॉइंट straight line तळे थांता सी गोटे मझरे straight line नहीं जानता. So deviation is more. R square term टा which most important should be nearly equal to 1, then you are happy that it is a linear good linear equation. Then I have found out del S by R is intercept, and from which I found that del S is equal to minus 13.7 joules per Kelvin per mole. There is a decrease in entropy during the process. And del H by R, this is del H by R is the slope, which is a negative slope. And from that we found that del H is equal to plus endothermic process. Minus minus becomes plus, and this will be 503 joules per mole. You understood? ଏବେ ତମେ ଟ୍ରାଏ କର ନିଜେ. ଆଚ୍ଛା କୋଉମାନେ ତମେ ଓମକାର ଶିଖିଛ ଏକ୍ସେଲ?
ବେସିକ ଗୁଡା ଜାଣିଛି କିନ୍ତୁ ଏଇ ସବୁ
କରିନ କାମ କରିନ ସମିଧା?
No, sir.
Okay, you will be knowing in your program, in your plus 2 ଭିତରେ ତମର ପଢେଇବ ସ୍କୁଲ ରେ ପଢେଇ ହବ. Okay then, so guys who are watching from the YouTube source, have a goodbye and see you on coming Monday. Please have a touch on our uranium website www.theuranium.in, where I used to post the link where you can get the YouTube link whenever you have next program. The next program, as I have already sounded you, I think none of you will be interested to join that. It will be too heavy.
No,
Rudra,
sir.
will you be
I will join,
interested?
sir. Yes, sir.
Omkar,
yes sir.
you decide. That will be a load to you. That is a 12th class program, and it will be a load to you. But if you are very happy and passionate about it, you can. Bye bye.
So it
And
will,
कौन कहलो ओमकार?
so when that program will start from?
No, that will be it will be an early morning program. You may
Sir,
not
No,
be
sir,
then no
available.
problem, sir.
It is
sir,
Indian early
date,
morning program.
sir,
Indian
date
early morning,
and
5 o'clock. What?
sir, date, like from which?
Maybe within 2 to 3 days after. After I complete your program, their program will start. Because once it is it's a public program, I have to be very careful in compiling the data and planning what to do and what to speak and what not to speak, so to to arrange things in order. Okay, bye. And those who are watching in YouTube, so don't hesitate to put a like button, and if you have not subscribed, please subscribe. Bye bye. My mouse is playing hide and seek today, and ତମେ ରହିଥାଅ, ମୁଁ ଟିକେ end କରିଦିଏ ଏପର୍ଯ୍ୟନ୍ତ end ହଉ। ତଳେ ଶେଷ କଲି। Okay. Okay, how did you like?
The